Floating in the darkness between stars, you find yourself surrounded by gas that is so thin you cannot see it, and dust that is so fine it blocks all visible light from beyond. The cold here is deeper than any cold you have experienced, around 15 Kelvin, which is 15 degrees above absolute zero, and the silence is complete. This is a molecular cloud, vast beyond comprehension, drifting through the galaxy for millions of years, and you have arrived here to witness something that happens rarely in any particular place. A star is about to be born from this darkness, and you will watch its entire life unfold from beginning to ultimate end. The blackness around you is not empty space, but rather a cloud of matter, mostly hydrogen molecules floating invisibly in the void, with smaller amounts of helium and microscopic grains of dust. You cannot see the gas itself because it emits no light, and the dust blocks any light that might illuminate it from outside. Stars exist beyond this cloud, but their light does not reach you here because the dust grains absorb and scatter the light before it penetrates this far. Only in infrared wavelengths could you see through this darkness to detect what lies within or beyond the cloud's boundaries. You are listening to the Drowsy Astronaut, and this is a slow journey through the complete life of a star, from its birth to its death and beyond. We will witness every stage together, staying with this one star through billions of years, and there is no hurry, because stellar time moves at a pace that makes human lifetimes invisible. If you are still awake later, feel free to share in the comments where you are listening from tonight. And if you enjoy this kind of slow exploration of real places in space, consider liking the video or subscribing to join us on future journeys. For now, we begin here in the dark. The cloud extends for dozens of light years in every direction, which means that light itself would take decades to cross from one side to the other. The material here has been drifting through space for perhaps 10 or 20 million years since it was expelled from older stars or collected from the interstellar medium. Most of the hydrogen exists as molecules, two hydrogen atoms bonded together, rather than as individual atoms, and this molecular form is what gives these clouds their name. The temperature of 15 Kelvin means the molecules move slowly, their thermal motion gentle in this profound cold. Around you float dust grains, each one smaller than a particle of smoke, composed of materials like carbon, silicates, and frozen water ice. These grains are so small that 100 of them placed side by side would barely equal the width of a human hair. The grains are spaced far apart in the general scheme of things, separated by distances large compared to their size. But compared to the space between stars, this cloud is relatively dense. The density here is about 100 to 1,000 particles per cubic centimeter, which sounds like a lot until you realize that air on Earth contains about 10 million trillion particles per cubic centimeter. Despite the low density, this cloud contains enough material to form thousands of stars if conditions allow, and the total mass might equal tens of thousands or even hundreds of thousands of suns. The matter is spread so thinly that you could move through it without feeling any resistance, and if you held out your hand, you would collect only a tiny number of molecules and dust grains. The cloud is more like a suggestion of matter than a substance. Yet gravity acts on every particle, and gravity will eventually compress this diffuse material into dense stellar cores. Nothing seems to be happening around you because the timescales here are so long that change is imperceptible over human observation periods. The molecules drift with slow, random motions determined by their temperature, and the dust grains move with the gas. The cloud has structure on large scales, with denser regions and less dense regions, filaments of slightly higher concentration threading through more diffuse areas. These density variations are small, perhaps a factor of 2 or 10 difference between denser and less dense regions, but they matter because gravity amplifies small differences. Somewhere nearby, though you cannot tell exactly where in the darkness, there is a region slightly denser than its surroundings, and gravity is beginning to pull material toward that region. The pull is incredibly weak because the cloud's density is so low and the distances are so vast, but gravity is patient and persistent. Every particle of matter attracts every other particle, and in a region where matter is slightly more concentrated, the combined gravitational pull of all that matter is slightly stronger. Material begins to drift toward the denser region, and as it does, the region becomes denser still. This is how stars begin, with the slightest density irregularity in a cold molecular cloud. A fluctuation that might have been caused by a shock wave from a nearby supernova or by the collision of two clouds, or simply by random chance. Once a region reaches a certain density, called the gene's mass, gravity overcomes the outward pressure from the gas, and collapse becomes inevitable. The cloud does not resist because the temperature is so low that the gas pressure is minimal, and nothing stops the inward fall. You are floating in a region that has just crossed this threshold, where gravity has begun to win against pressure, and collapse has started, though it is still imperceptible to direct observation. The material around you is beginning to move, accelerating inward toward the center of the collapsing region, but the acceleration is measured in millimeters per year at this early stage. Detecting the motion requires patience, or instruments that can measure tiny velocity shifts through the Doppler effect in spectral lines. The collapsing region is large, perhaps a few light years across initially, containing enough material to form not just one star, but perhaps dozens or hundreds. Within this larger region, smaller subregions are also collapsing, each one destined to form an individual star or a small group of stars. The hierarchy of collapse creates structure, with dense cores forming within collapsing clumps, within collapsing clouds, and each level operates on its own timescale, determined by its density and size. The dust grains that float around you play an important role despite their small size, because they shield the interior of the cloud from external radiation and allow the gas to cool. If the gas could not cool, pressure would build up and resist collapse. But when gas cools, it loses energy and the pressure drops. The dust also provides surfaces where molecules can form, hydrogen atoms meeting on a dust grain's frozen surface and bonding into hydrogen molecules. Without dust, molecular clouds would be very different, and star formation would be less efficient. Around you in the darkness, other stars are forming or have recently formed, though you cannot see them through the dust that obscures visible light. Infrared observations would reveal bright spots where protostars are already condensing, their heat making them visible in wavelengths that penetrate dust better than optical light does. Some of these forming stars will eventually illuminate the cloud from within, ionizing gas and creating glowing nebulae. But that will happen later, after they ignite fusion in their cores. The silence here is absolute, because sound requires a medium dense enough to transmit pressure waves, and this cloud, while denser than interstellar space, is still far too tenuous to carry sound in any meaningful way. You could shout, and the sound would not travel even a short distance because there are not enough collisions between particles to propagate the wave. The cloud exists in complete acoustic isolation, every region silent to every other region, communication possible only through light or gravity. Time passes, though you cannot tell how much, because there are no reference points and no change visible to your eyes in the surrounding darkness. Days or years or centuries could go by, and the view would remain the same, the slow inward drift of material too gradual to detect directly. The collapse timescale for a region like this is roughly 100,000 years, which means the material will take that long to fall from the outer edges to the center. That is fast by stellar standards, but inconceivably slow by human standards. Gradually, over what would be thousands of years if you waited in real time, the motion around you becomes slightly more noticeable, the inward drift accelerating as the collapsing region becomes smaller and denser. The material is falling freely now under gravity's pull, no longer floating passively, but actively streaming toward the center. You begin to move with the infalling material, falling inward alongside the hydrogen molecules and dust grains, all of you drawn toward the same destination. The collapse has progressed from imperceptible to slow but measurable, and the journey toward the center has truly begun. The infall continues, and you are now moving noticeably inward, along with the surrounding gas and dust, toward the center of the collapsing region. Around you, material is converging from all directions, streams of gas and dust, all falling toward the same point in space ahead. The collapse is no longer a theoretical process, but a visible flow of matter moving through the darkness. The density around you increases as material from a larger volume compresses into a smaller space, and the increase in density brings a slow rise in temperature. When gas is compressed, it heats up because the gravitational potential energy of the falling material converts into thermal energy as particles collide more frequently. The temperature is still very cold by any reasonable standard, perhaps 20 or 30 Kelvin now instead of 15. But the trend is clear. As the collapse continues, the center will heat faster than the outer regions because it experiences more compression. Looking ahead in the direction you are falling, you can sense that the center is becoming denser, even though you cannot see it directly through the surrounding dust. Instruments would show that the center is now perhaps 100 times denser than the cloud was initially, and it continues to densify as material pours in. The central region is still far too diffuse to be considered a solid object or even a distinct entity, but it represents the beginning of what will become the star's core. The rotation comes from the fact that the original cloud had some overall spin, even if very slight, and as material falls inward, it must spin faster to conserve angular momentum. This is the same principle that causes figure skaters to spin faster when they pull their arms inward. And it applies to collapsing gas clouds, just as it applies to spinning skaters. The rotation manifests as a slow wheeling motion, material orbiting the center as it falls, and the combination of inward motion and circular motion creates a spiral pattern. You are part of this spiral now, falling inward but also moving sideways in an orbital sense, and the material around you is doing the same. The fastest rotation occurs closest to the center, where material that has fallen the farthest must spin the fastest, and this creates a velocity gradient across the collapsing region. As the collapse continues and rotation becomes more important, material begins to settle into a disc shape, rather than falling in spherically from all directions. The disc forms perpendicular to the rotation axis, because material falling from above or below the disc collides with material already in the disc and loses its vertical motion. The result is a flattened structure, thicker in the center and thinner at the edges, with material orbiting in roughly the same plane. This disk is the protoplanetary disk, though planets are far in the future, and it surrounds the forming protostar at the center. You are now within the disk, orbiting the center, along with gas and dust, and the view has changed from featureless darkness to a structured environment with a definite orientation. There is an up and down defined by the disk's rotation axis, and there is an in and out defined by the distance from the center. The disk extends for hundreds of astronomical units potentially, with the densest material concentrated within the inner tens of AU, where the star is forming. Ahead of you, toward the center, the condensation is becoming warmer and denser, and it has started to glow faintly in infrared wavelengths from the heat of compression. The center is now distinct enough to be called a protostellar core, a concentration of gas and dust that will become the star. The core's temperature has risen to perhaps a few hundred Kelvin at its center, warm enough to vaporize some of the ice mantles on dust grains, but still far too cold for fusion. Material continues to rain onto the protostellar core from the surrounding disk, and the core grows larger and denser as it accretes mass. The infall rate is substantial, perhaps 1/10,000th of a solar mass per year, which means the core is gaining mass equivalent to Earth every few years. This accretion releases gravitational energy as material falls into the deepening potential well, and that energy heats the core further. The heating is gentle but continuous, and the core's temperature climbs slowly as more material accumulates. The timescale of the collapse has shortened now compared to the initial freefall phase, because some of the material has settled into the disk and is no longer falling directly inward. Material in the disk spirals inward gradually, losing angular momentum through friction with surrounding gas and through magnetic fields that thread through the ionized portions of the disk. The process is slower than free fall, and it will take longer for disk material to reach the star than it took for the initial collapse to create the disk. Around you in the disk, dust grains are colliding and sometimes sticking together, beginning the slow process of planet formation that will take millions of years. The grains are still small, but they grow through gentle collisions, snowflakes of ice and rock accumulating into larger particles. This process is tangential to the star's formation, but will eventually produce the planets that orbit the star, and it is happening all around you in the disk as you spiral inward. The collapsing region has structure now, very different from the formless darkness where the journey began, and the structure is dynamic, with material moving in organized patterns. There is the central protostellar core, warm and dense and growing. There is the disk surrounding it, rotating and spiraling inward, feeding material to the core. There are the regions above and below the disk, where material is still falling inward from the larger cloud, adding mass to the system. All of this is hidden from outside observers by the surrounding envelope of dust. But from inside, the activity is evident. Looking back toward the outer regions of the disk and beyond, you can see that material is still falling inward from the larger molecular cloud, and the collapsing region is still accreting from its surroundings. The boundary between the collapsing region and the general cloud is not sharp, but rather gradual, a transition zone where material is beginning to feel the pull of the central concentration. The system is pulling in matter from a region perhaps a light year across, gathering the material that will eventually form the star and its planets. The journey inward continues, and as you spiral closer to the protostellar core, the temperature around you increases, and the density rises further. The disk is warmer toward the center, heated by the radiation from the protostellar core and by the friction of material spiraling inward. Closer to the core, the temperature might reach hundreds or even 1,000 Kelvin, warm enough that water ice cannot exist, and only rocky materials and metals remain solid. Farther out where you are currently, ice is still stable, and the dust grains are coated with frozen water and other volatiles. The magnetic field in the collapsing region has strengthened as the material has compressed, and the field now plays an important role in the dynamics of the system. The field threads through the disk and connects the disk to the protostellar core, and it acts like a brake on the rotation, allowing angular momentum to be transferred outward while material moves inward. Without this magnetic braking, the rotation would spin the disk so fast that material could not reach the center, and the star would not be able to grow. Time continues to pass, measured now in thousands of years, and the protostellar core at the center continues to grow and heat. The temperature at the core's center has climbed to several thousand Kelvin, hot enough that the core glows brightly in infrared light. The core is still far from fusion conditions, but it is no longer a cold condensation. It is a hot, dense ball of gas, held together by gravity and heated by the continuous inflow of material. The protostar is forming. You have fallen far from the outer regions where the journey began, and the environment has changed completely from cold, featureless darkness to a structured disk with a warm, glowing center. The star is not yet born in the sense that fusion has not ignited, but the protostar exists as a distinct object, and it is growing toward the mass and temperature needed for fusion. The collapse has brought you to the heart of the forming system, and the next phase of stellar birth is about to begin. The protostellar core ahead has grown large enough and distinct enough that it now appears as a definite object rather than just a concentration in the gas, and you are approaching it from within the surrounding disk. The protostar glows with a dull red-orange light, visible now even in wavelengths your eyes could detect if you were actually here. And the glow comes from the heat generated by gravitational compression. The surface temperature of the protostar is around 3,000 to 4,000 Kelvin. Cool by stellar standards, but hot enough to make the object shine. The protostar is larger than the star it will eventually become, swollen by the energy of infill and not yet contracted to its final size. Material continues to fall onto the protostar from the disk around it, and you can see streams of gas spiraling inward and striking the protostar's surface at the equator where the disk meets the star. The impact of infalling material creates hot spots on the surface where the kinetic energy of the gas converts to heat, and these regions glow brighter than the surrounding surface. The infall rate varies over time, sometimes faster and sometimes slower, causing the protostar's brightness to fluctuate. These fluctuations happen over years or decades, rapid by stellar standards, but still slow by human perception. The protostar is embedded within a cocoon of gas and dust that surrounds it in all directions, material that has not yet fallen onto the star or been incorporated into the disk. This envelope makes the protostar invisible to outside observers looking in optical light, because the dust absorbs all the visible photons and re-radiates the energy in infrared wavelengths. From outside, the system would appear as a dark spot or a faint infrared source. But from inside, you can see the protostar clearly because you are within the envelope looking at the star directly. The protostar's size is difficult to judge precisely because its surface is not sharply defined, the hot, dense center fading gradually into the cooler, infalling envelope. But the radius is perhaps 5 to 10 times larger than the Sun's radius. The mass is still growing, currently perhaps half a solar mass or so, and it will continue to accrete until the surrounding material is exhausted or blown away. The final mass of the star depends on how much material is available and how efficient the accretion process is. And for this particular protostar, the final mass will be close to the Sun's mass. Looking away from the protostar toward the poles above and below the disk, you can see something remarkable. Jets of material being ejected from the vicinity of the protostar in narrow beams perpendicular to the disk. These jets are fast-moving streams of gas, traveling at tens or hundreds of kilometers per second, and they extend for tremendous distances beyond the protostar's immediate vicinity. The jets are collimated, meaning they stay narrow rather than spreading out, and they plow through the surrounding envelope and out into the larger molecular cloud beyond. The jets are visible where they shock heat the surrounding gas, creating glowing regions called Herbig-Haro objects, far from the protostar. The mechanism that creates the jets involves the magnetic field that threads through the disk and connects to the protostar, and the rotation of the system twists the field and accelerates gas outward along the poles. The details are complex, but the result is clear. The protostar is not just pulling material in, but also expelling some of it in highly directed outflows. These jets carry away angular momentum and help solve the problem of how material can fall onto the star, despite rotation. Without the jets, the accumulating angular momentum would spin the system faster and faster until centrifugal force prevented further infall. The disk around the protostar is more substantial now than it was during the earlier collapse phase, and it contains a significant fraction of the system's total mass. The disk is warmest near the protostar, where temperatures reach 1,000 Kelvin or more, and coolest at the outer edges, tens or hundreds of AU away, where temperatures drop below 100 Kelvin. This temperature gradient creates different zones in the disk, where different materials can condense, ice lines marking the boundaries where various volatiles freeze out of the gas phase. You are orbiting within the disk at a distance of perhaps 10 or 20 ATU from the protostar, far enough that the temperature is moderate and water ice is stable on dust-grained surfaces. The disk here is thin compared to its radius, perhaps 1/10 as thick as it is wide, and the material is concentrated in the midplane with density falling off above and below. The gas and dust move together, orbiting the protostar in the same direction, and collisions between particles keep the motion organized and prevent the disk from puffing up. The protostar's gravity dominates the region, and everything orbits according to Kepler's laws, with inner material orbiting faster than outer material. From your position, the protostar appears to remain in the same direction, neither ahead nor behind, because you are orbiting at the speed appropriate for your distance. Material closer to the protostar orbits faster and would appear to move ahead, while material farther out orbits slower and would appear to fall behind. This differential rotation creates shear in the disk, which generates friction and turbulence. The environment around you is not static, but dynamic, with gas and dust moving in complex patterns influenced by gravity, rotation, magnetic fields, and turbulence. Small eddies and vortices form in the disk, transporting material and angular momentum, and waves propagate through the gas, creating density variations. The disk is alive with motion on all scales, from the thermal motion of individual atoms to the large-scale spiral structures that may form when the disk is massive enough to feel its own gravity. The protostar itself is slowly contracting as gravity pulls it inward, and this contraction heats the interior further. The center of the protostar is now perhaps 100,000 Kelvin, far hotter than the surface, and the temperature continues to climb as the protostar contracts. The core is still nowhere near the 15 million Kelvin needed for hydrogen fusion, but the trend is clear and inevitable. Unless something stops the contraction, the core temperature will eventually reach fusion conditions, though this will take another million years or more. The energy that powers the protostar's glow comes from the conversion of gravitational potential energy into heat, a process called Kelvin-Helmholtz contraction. As the protostar shrinks, material falls deeper into its gravitational well, and the potential energy released appears as heat that makes the protostar shine. This mechanism can power the protostar for millions of years, but it is not sustainable indefinitely. Eventually, the contraction will slow, and fusion must take over, or the protostar will cool and fade. Around the forming star system, other protostars are likely forming from the same molecular cloud, siblings being born from the same parent material, and some of them might eventually become gravitationally bound to this star in a multiple star system. Most stars form in clusters, groups of dozens or hundreds of stars born together, and they spend their early lives in close proximity before drifting apart as the cluster dissolves. This protostar is part of that larger birth process, one member of a generation of stars emerging from the cloud. The disk around the protostar will eventually become the birthplace of planets, if the disk survives long enough and contains enough material. Dust grains are already colliding and sticking together, growing from microscopic particles into larger aggregates. And this process will continue for millions of years. Eventually, some of the aggregates will grow large enough to gravitationally attract additional material, becoming planetesimals, and then protoplanets. But that is far in the future. And for now, the disk's main role is feeding the growing protostar. The protostellar phase is a transition between the initial collapse and the eventual ignition of fusion, and it lasts for a substantial fraction of the total formation time. The protostar must gain enough mass, contract enough to heat its core, and wait for the temperature to climb to fusion conditions. The waiting period is long by human standards, millions of years. But it is a necessary stage in the star's development. You are witnessing the protostar in the middle of this phase, already well formed but still far from becoming a true star. The light from the protostar illuminates the inner portions of the disk, creating a visible environment where before there was only darkness. The glow is reddish-orange, the color of relatively cool emission, and it casts soft light on the gas and dust around it. Shadows form where dense clumps in the disk block the light, and the shadows stretch outward in the radial direction. The scene has a dim beauty, a forming star system in its infancy, complex and active, and slowly progressing toward the next phase. Time continues its slow march forward, and the protostar continues to accrete and contract, the two processes happening simultaneously. The surrounding envelope of gas and dust gradually disperses as material either falls onto the star and disk or is blown away by the jets and the developing stellar wind. Eventually, the envelope will clear enough that outside observers could see the protostar directly, and it will transition from an embedded source to a visible pre-main sequence star. That transition is beginning to happen now, as the cocoon thins and the protostar's light starts to escape. The protostar has continued to grow and contract over the past million years, and you have remained in its vicinity to witness the slow changes that accumulate over immense timescales. The core temperature has climbed steadily from 100,000 Kelvin to several million Kelvin, and the density in the center has increased to levels where matter is compressed far beyond anything found on Earth. The protostar's mass is now approximately 1 solar mass, similar to what the Sun's mass will be, and it has nearly finished accreting material from the surrounding disk. The infall has slowed because the disk is being depleted, and because the protostar's strengthening stellar wind is beginning to push material away rather than allowing it all to fall inward. Deep in the protostar's core, conditions are approaching the threshold where nuclear fusion becomes possible, and the core temperature is now close to 10 million Kelvin. At these temperatures, protons, hydrogen nuclei, move fast enough that when they collide, they sometimes come close enough for the strong nuclear force to bind them together despite their electromagnetic repulsion. The collisions are still rare at 10 million Kelvin, and fusion reactions are not yet self-sustaining, but the occasional fusion event does occur, a preview of what will soon become the star's main energy source. You are floating at a safe distance from the protostar, far enough that the heat and radiation are manageable, but close enough to observe the surface and the activity around it. The protostar has changed appearance over the long waiting period, becoming smaller as it contracts and hotter at the surface as gravitational energy continues to compress it. The surface temperature is now around 5,000 Kelvin, and the color has shifted from red-orange to yellow-white. The protostar resembles a young star, though fusion has not yet stabilized in the core. The core temperature creeps upward, 13 million Kelvin, 14 million Kelvin, and the density continues to increase as gravity compresses the center. The electrons in the core have been stripped from their atoms by the intense heat, creating a plasma of bare nuclei and free electrons. And the nuclei collide constantly in their thermal motion. Most collisions simply bounce the nuclei off each other, but occasionally, two protons approach close enough to fuse, and when they do, a cascade of reactions can follow. The fusion of hydrogen into helium follows a sequence called the proton-proton chain, and it requires multiple steps. Two protons fuse to form deuterium, one proton and one neutron, and the deuterium then fuses with another proton to form helium-3, two protons and one neutron. Two helium-3 nuclei collide and fuse to form helium-4, two protons and two neutrons, releasing the two extra protons back into the plasma. The net result is that four protons become one helium nucleus, and the mass of the helium nucleus is slightly less than the mass of four protons. The missing mass has been converted into energy, according to Einstein's equation, E equals mc squared. The core temperature reaches 15 million Kelvin, and the fusion rate suddenly increases as more and more proton collisions have enough energy to overcome the electromagnetic barrier. The energy released by fusion starts to add noticeable heat to the core, and this additional heat increases the pressure, which pushes outward against gravity. For the first time in the protostar's life, an energy source other than gravitational contraction is generating heat, and the balance of forces within the star begins to shift. The moment of ignition is not a sudden dramatic event visible from outside, but rather a gradual transition that happens over thousands of years as fusion becomes increasingly important. The fusion reactions in the core generate energy. The energy heats the surrounding material. The heat increases the pressure, and the pressure slows the contraction. Eventually, the outward pressure from the heat of fusion balances the inward pull of gravity, and the star reaches a stable configuration where neither contraction nor expansion dominates. This equilibrium is called hydrostatic balance, and it marks the beginning of the main sequence phase. You watch as the protostar settles into this new state, the contractions slowing and then stopping altogether, the surface ceasing to grow brighter, the luminosity stabilizing at a steady value. The star is now generating energy in its core at the same rate it radiates energy from its surface, and the energy flow is in balance. The temperature and pressure at each point inside the star are precisely what they need to be to support the weight of the layers above, and the system is stable against perturbations. The stellar wind that was already present during the protostellar phase now strengthens as the star's radiation output stabilizes and increases, and the wind begins to clear away the remaining gas and dust in the inner regions of the disk. The wind is a stream of charged particles, electrons and protons, flowing outward from the star's surface, accelerated by the pressure of radiation and the star's magnetic field. The wind pressure pushes against the disk material, and gradually it sweeps the inner disk clean of gas, though solid particles, dust and larger, can resist the wind's push somewhat longer. Looking toward the star, You can see that the cocoon of infalling material that surrounded it during the protostellar phase has largely dispersed, blown away by the wind and the jets, and exhausted by accretion. The star is now visible in optical light from any direction, no longer hidden by dust, and it would appear to outside observers as a young star surrounded by a disk. This is the classical T-Tauri phase for stars of this mass, named after the prototype star T-Tauri in the constellation Taurus. The star has reached the zero-age main sequence, the beginning of its long, stable phase of hydrogen burning, and it will remain in this configuration for billions of years. The fusion reactions in the core are self-sustaining now, and they generate enough energy to maintain the temperature and pressure needed for the reactions to continue. The star has become a true star in every sense, no longer a protostar or a pre-main sequence object, and it has joined the population of stars in the galaxy. The transition from protostar to main sequence star has taken several million years in total from the beginning of the collapse in the molecular cloud, and the timescale was determined by the star's mass and the properties of the molecular cloud. More massive stars evolve faster through these stages because their stronger gravity compresses them more quickly and heats them to fusion temperatures sooner. Less massive stars take longer, sometimes tens of millions of years to reach the main sequence. This star, with mass similar to the Sun, took about 5 to 10 million years from collapse to ignition. The disk around the star has changed as well during this transition, thinning as material either accreted onto the star or was blown away by the wind. The inner regions of the disk, within a few AU, are now largely free of gas, though dust and larger particles remain. And these solid materials are continuing their slow accumulation into larger bodies. The outer regions of the disk, beyond tens of AU, still contain gas and dust, and they will persist for several more million years before being dispersed or incorporated into planets. The star's surface shows features now that were not present during the protostar phase, including dark spots where magnetic fields suppress convection and create cooler regions analogous to sunspots. The magnetic field itself is strong and complex, generated by the motion of conducting plasma inside the star, and it creates active regions on the surface where energy is released in flares and other phenomena. The star is young and active, more so than it will be later in life, and its magnetic activity affects the surrounding disk and any forming planets. From your vantage point, you can see the star shining steadily now, with a yellow-white light, its luminosity constant, rather than fluctuating as it did during the protostellar phase. The flux of energy from the star's surface is continuous and reliable, and this energy flows outward into space, warming the disk and providing light that reflects off dust grains. The star has emerged from its birth process and is now entering the longest phase of its existence, the main sequence, where it will burn hydrogen in its core for 10 billion years. The jets that characterize the protostellar phase have weakened or stopped now that accretion has largely ceased, and the bipolar outflows are no longer visible. The stellar wind has replaced the jets as the primary way the star interacts with its environment, and the wind fills the space around the star with a tenuous plasma flowing outward at hundreds of kilometers per second. This wind will continue throughout the star's main sequence life, though it may weaken somewhat as the star ages and its magnetic activity declines. The ignition of fusion and the establishment of hydrostatic equilibrium represent a fundamental change in the star's nature, from an object powered by contraction to an object powered by nuclear reactions. The energy source will sustain the star for a time longer than the entire history of complex life on Earth. And during that time, the star will barely change in luminosity or surface temperature. The stability is remarkable, a consequence of the self-regulating nature of fusion reactions and the way the star responds to small perturbations by adjusting its structure to maintain balance. You have witnessed the birth of a star, from the cold molecular cloud where the journey began, to the ignition of fusion and the start of the main sequence phase. The timescale compressed from millions of years into this observation has shown how gravity collects matter, how compression generates heat, and how fusion eventually takes over as the star's power source. The star now burns with the light of fusion, and it will continue burning for billions of years before the next phase of its life begins. The star has settled into its main sequence configuration, and from your position, observing at a comfortable distance, it appears remarkably stable and unchanging. The surface glows with steady yellow-white light, the same color it will show for billions of years, and the luminosity remains constant from year to year. The star's radius is similar to what the sun's radius is, about 700,000 kilometers, and its mass is approximately 1 solar mass. Everything is in balance now, gravity pulling inward and pressure pushing outward with equal force, and the star is neither contracting nor expanding. Deep in the core, where you cannot directly see, hydrogen is fusing into helium continuously, and the reactions generate energy that flows outward through the star's interior. The core temperature has stabilized at around 15 million Kelvin, exactly the temperature needed to sustain fusion at the rate required to balance the star's energy output. The core density is about 150 grams per cubic centimeter, roughly 10 times denser than lead. And at this density, the hydrogen nuclei are packed close enough that fusion collisions happen frequently, despite the electromagnetic repulsion between protons. The fusion process converts mass into energy at a rate of about 4 million tons per second, which sounds enormous, but represents only a tiny fraction of the star's total mass. The star has a mass of about 2 times 10 to the 30 kilograms, and losing 4 million tons per second means it will take billions of years to consume a significant fraction of its hydrogen fuel. The energy released by fusion travels outward from the core through the star's interior, and this energy is what eventually emerges as the starlight that illuminates planets and dust. The energy transport from core to surface happens through 2 mechanisms depending on the depth inside the star: radiation and convection. In the inner portion, including the core, energy moves outward through radiation, with photons traveling short distances before being absorbed and re-emitted by atoms in the hot plasma. A single photon generated in the core takes hundreds of thousands of years to random walk its way to the surface, absorbed and re-emitted countless times. In the outer portion of the star, energy moves through convection, with hot gas rising to the surface, cooling, and then sinking back down in a continuous circulation pattern. You observe the star over what would be thousands or millions of years in compressed time, and the changes are subtle but present. The luminosity increases slightly as the star ages, rising by perhaps 1% every 100 million years. And this increase happens because helium ash is accumulating in the core and changing its composition. Helium is heavier than hydrogen, and as it builds up the core, becomes denser and contracts slightly. The contraction heats the core a bit, and the fusion rate increases slightly, leading to higher luminosity. The star's surface shows active regions where magnetic fields break through and create spots and flares, and these features come and go on timescales of days to years. The magnetic activity follows a cycle, with periods of high activity alternating with periods of low activity. And the cycle length is about 11 years, similar to the solar cycle. During active periods, the star's surface is dotted with dark spots where strong magnetic fields suppress convection and cool the surface locally. During quiet periods, the surface is smoother and more uniform. Looking inward toward the core in your mind's eye, using understanding rather than direct sight, you can track the changing composition as hydrogen converts to helium. The core started as essentially pure hydrogen, about 70% by mass, with the remaining 30% mostly helium left over from the Big Bang. As fusion proceeds, the hydrogen fraction in the core decreases and the helium fraction increases. After 1 billion years, the core might be 60% hydrogen and 40% helium, and after 5 billion years, the fractions might be more equal. The helium produced by fusion cannot undergo fusion at the current core temperature of 15 million Kelvin, because helium nuclei have a higher electrical charge and repel each other more strongly than hydrogen nuclei do. Fusing helium requires temperatures around 100 million Kelvin, far hotter than the current core temperature, so the helium simply accumulates as an inert ash in the center. This accumulation will eventually become important when the core's hydrogen runs low, but that is billions of years in the future. The star's main sequence lifetime depends critically on its mass, and for a star of one solar mass, like this one, the lifetime is about 10 billion years. More massive stars burn their hydrogen much faster and have shorter main sequence lives, sometimes only a few million years for the most massive stars. Less massive stars burn more slowly and can remain on the main sequence for hundreds of billions of years, far longer than the current age of the universe. This star, being Sun-like, falls in the middle range with a respectable 10 billion year lifetime. The surrounding disk has continued to evolve during the star's early main sequence phase, and by the time the star is a few hundred million years old, the disk has largely dispersed. Gas has been blown away by the stellar wind or has accreted onto the star, and much of the dust has either fallen into the star or been incorporated into solid bodies. Planets have likely formed from the disk material, rocky planets in the inner regions and gas giants farther out, where volatiles could condense, though the planets are too small and faint to see easily from your vantage point. The star's position in the galaxy is not static, and it orbits the galactic center along with billions of other stars, taking about 200 million years to complete one orbit. The star was born in a cluster along with siblings, but over time the cluster disperses as stars drift apart due to gravitational interactions and the galaxy's differential rotation. After a few hundred million years, the star may no longer be near its birth siblings, though they all share a similar age and composition. Time continues to flow, and the star continues to burn hydrogen in its core with remarkable consistency, year after year, century after century, millennium after millennium. The timescale is so long that entire civilizations could rise and fall on any planets orbiting the star, without the star itself changing perceptibly. From the star's perspective, the passage of human timescales is essentially instantaneous, too brief to matter in the slow rhythm of stellar evolution. The hydrogen burning phase is the longest and most stable period of the star's life. And during this time, the star contributes to the galaxy's light and to the enrichment of the interstellar medium through its stellar wind. The wind carries away a tiny amount of the star's mass, perhaps 1/10 trillionth of a solar mass per year, which is negligible compared to the star's total mass, but adds up over billions of years. The wind also carries the star's magnetic field outward into space, creating a bubble of magnetized plasma around the star. Observing the star from outside, astronomers would classify it as a G-type main sequence star, often called a yellow dwarf, and they would note its similarity to the Sun in mass, radius, temperature, and luminosity. The star is unremarkable by galactic standards, one of billions of similar stars, but it is precisely this type of star that has proven capable of hosting planets with complex life. The stability and longevity of such stars provide billions of years for planetary atmospheres to develop and for life to emerge and evolve. The core temperature and fusion rate are in a delicate balance, maintained by the star's response to any changes. If the fusion rate increases, the core heats up, the pressure rises, and the core expands slightly. The expansion cools the core and reduces the fusion rate back to the equilibrium value. If the fusion rate decreases, the opposite happens. The core cools, contracts, heats up again, and the fusion rate increases. This thermostat mechanism keeps the star stable against perturbations. You watch as billions of years pass in compressed observation, the star barely changing in appearance, but steadily converting hydrogen to helium in its core. The luminosity increases by about 30% over the course of the main sequence, brightening gradually as the core composition shifts and the fusion rate adjusts. This brightening is slow enough that planets can adapt if they have active geology and atmospheric regulation, but it is real and measurable over billions of years. The star is now about halfway through its main sequence lifetime, 5 billion years old, and the core hydrogen fraction has dropped noticeably from the initial 70% to perhaps 40 or 50%. The helium ash in the center is building up, and the fusion reactions are now happening in a shell around the helium-rich center, rather than uniformly throughout the core. The transition from a uniform burning core to a shell-burning configuration is gradual, but it marks the beginning of the end of the main sequence phase. Around the galaxy, other stars born at the same time as this one are also progressing through their main sequence lives, and some of the more massive siblings have already died, exploding as supernovae or shedding their envelopes to become white dwarfs. Less massive siblings are still early in their main sequence phase and will continue for hundreds of billions of years more. The diversity of stellar timescales means that a single generation of stars experiences very different lifetimes, depending on their individual masses. The stable main sequence phase is drawing toward its eventual end, though the end is still billions of years away in real time. The star will continue to shine steadily, converting hydrogen to helium, supporting any life that may have developed on its planets, and contributing to the galactic ecosystem of stars and gas. But the hydrogen fuel is finite, and eventually the core will run low, and the star will have to transition to a new phase of life. That transition is beginning to approach as the core hydrogen dwindles. The star has aged considerably since the main sequence began, and approximately 9 billion years have passed since fusion first ignited in the core. The hydrogen in the core has been steadily depleted, and the fusion reactions that once occurred throughout the central region are now concentrated in a shell around the core's center. The very center of the star contains mostly helium, the ash from billions of years of hydrogen fusion, and this helium cannot fuse at the current temperature of around 15 million Kelvin. The helium core sits inert at the star's center, no longer generating energy, and it slowly grows as the surrounding hydrogen shell continues to fuse and add more helium to the core. From your observing position, the star still appears much as it did during the main sequence, yellow-white and steady, but subtle changes are beginning to accumulate. The luminosity has increased by about 40% from the star's zero-age main sequence value, and the surface temperature has risen slightly as well. These changes reflect the internal reorganization happening as the core transitions from uniform hydrogen burning to shell burning around an inert helium core. The helium core is contracting under its own gravity because it no longer has fusion energy to support it against gravitational collapse. The contraction of the helium core releases gravitational energy, and this energy heats the core and the surrounding layers. The hydrogen burning shell around the core experiences this heating, and the higher temperature makes the fusion reactions in the shell proceed faster than they did when fusion occurred in the core. The shell burning is more efficient than core burning was, and the star's total energy output increases. This seems counterintuitive, the star brightening as it runs out of fuel, but it is a consequence of the core contraction and the resulting temperature increase in the burning shell. The increased energy output from the shell causes the star's outer layers to expand, and over millions of years, the star's radius begins to grow beyond its main sequence size. The expansion is gradual at first, perhaps 10 or 20% over hundreds of millions of years, and the surface temperature drops slightly as the energy is spread over a larger area. The star is transitioning off the main sequence onto what astronomers call the subgiant branch, the evolutionary phase between the main sequence and the red giant phase. Looking inward at the structure, you can see the layered configuration developing inside the star. At the center is the inert helium core, roughly 10% of the star's total mass, contracting and heating, but not fusing. Around the helium core is the hydrogen burning shell, a thin region where fusion still proceeds, generating energy and adding helium to the core from below. Above the burning shell is a thick envelope of hydrogen-rich material that is not hot or dense enough to fuse, and this envelope extends to the star's surface. The star has developed an onion-like structure with distinct layers. The helium core continues to contract as gravity pulls it inward, and the contraction accelerates as the core's mass increases from ongoing shell burning. The core temperature rises from 15 million Kelvin toward higher values, climbing past 20 million and then 30 million Kelvin as the decades and centuries pass. The density also increases dramatically, and the helium nuclei and free electrons in the core become so densely packed that quantum mechanical effects start to matter. The electrons enter a state called degeneracy, where they are forced so close together that quantum mechanics creates a pressure independent of temperature. This electron degeneracy pressure is different from normal gas pressure, which depends on temperature, and it arises from the Pauli exclusion principle that prevents electrons from occupying the same quantum state. In a degenerate gas, the electrons are packed as tightly as quantum mechanics allows, and further compression requires enormous force. The degenerate pressure helps support the core against gravity, even as the core continues to contract and heat, and this pressure will become important later when helium fusion ignites. The hydrogen-burning shell continues to add helium to the core, and the core's mass grows slowly, perhaps doubling over the course of 1 billion years. The increasing mass makes the core contract more, which heats it further, which makes the shell burn faster, which adds helium faster. This feedback process causes the star's evolution to accelerate, and the changes that took billions of years during the main sequence now take only hundreds of millions of years. The star is running downhill, energetically, progressing faster and faster through its remaining stages. The star's surface has expanded noticeably now, and the radius is perhaps twice what it was on the main sequence, making the star physically larger than before, even though its mass has barely changed. The luminosity has increased as well, perhaps 3 or 4 times the main sequence value, and the star shines brighter than it did in its youth. The surface temperature has dropped slightly from the expansion, but the increased surface area more than compensates, so the total light output is higher. Observing the star now, you would notice that its color has shifted slightly, from yellow-white toward orange, as the surface temperature drops below 6,000 Kelvin. The star is becoming a subgiant, larger and brighter than a main sequence star, but not yet the enormous red giant it will become. The transition is steady rather than abrupt, and the star smoothly evolves from one state to the next without discontinuities. The core temperature continues its climb, passing 50 million Kelvin and approaching 100 million Kelvin, the threshold where helium can begin to fuse. The core is now about 100 times denser than water, and the helium nuclei are separated by only a few nuclear diameters. The electrons provide degeneracy pressure that supports the core, but the helium nuclei themselves are still behaving like a normal gas, moving with thermal velocities determined by the temperature. The hydrogen-burning shell has moved outward in mass as it consumes fuel, and it now sits farther from the center than it did initially. Below the shell, the helium core continues to grow, and above the shell, the hydrogen envelope remains untouched by fusion. The shell is thin, perhaps only a few % of the star's radius, but it generates most of the star's energy. The contrast between the thin, energy-generating shell and the vast inert envelope is striking. The star's luminosity continues to increase as the shell burning intensifies and the outer envelope continues to expand in response. The expansion accelerates as the core contracts faster, and the radius grows from twice the main sequence value to 3 times and then 5 times. The surface temperature drops correspondingly, falling from 6,000 Kelvin toward 5,000 and then 4,000 Kelvin. The star is transitioning from subgiant to red giant, and the changes are happening faster now. Time passes more quickly from the star's perspective now, and what took billions of years during the main sequence now takes only hundreds of millions. The core's helium mass has grown to about 25% of the star's total mass, and the core temperature approaches the critical value of 100 million Kelvin. The core is supported almost entirely by electron degeneracy pressure now, and the temperature has become decoupled from the pressure. This will have important consequences when helium ignition occurs. Looking at the star from outside, you see an object much larger and more luminous than the main sequence star it was, with a surface glowing orange-red rather than yellow-white. The star has left the main sequence behind and is ascending the red giant branch, growing larger and brighter with each passing million years. The fuel in the core is exhausted, but the shell burning provides ample energy, and the star shines brightly despite having no central fusion. The transition from main sequence to red giant is well underway, and the next dramatic change is approaching as the core heats toward helium ignition. The surrounding space has changed as well, with any planets that orbited close to the star now engulfed by the expanding envelope, or at least experiencing intense heating from the star's increased luminosity. Planets that were once temperate are now scorched, and planets that were once frozen are now warmed. The star's evolution affects its entire planetary system, and the changes are dramatic for any worlds that might have hosted life. The star's aging is not just an internal process, but has external consequences for everything in its vicinity. The star's mass has decreased slightly from the stellar wind that has blown continuously throughout its life, carrying away perhaps 10% of the original mass over billions of years. The mass loss accelerates as the star becomes a giant, with the tenuous outer layers more easily stripped away by radiation pressure and stellar wind. The lost material drifts into space, enriching the interstellar medium with hydrogen and helium and traces of heavier elements created in the star's interior and brought to the surface by convection. You watch as the star continues to swell, the radius approaching 100 times its main sequence value, and the surface temperature dropping toward 3000 Kelvin. The star is now a full-fledged red giant, enormous and luminous, with an inert helium core that is poised on the brink of ignition. The core temperature is approaching 100 million Kelvin, and the moment when helium fusion begins is only a few million years away. The star's transformation from main sequence to red giant is nearly complete, and the next major event in its life is about to occur. The star is now a red giant, and from any reasonable distance, it appears enormous, its surface extending far beyond where the inner planets once orbited during the main sequence phase. The radius has grown to approximately 100 times what it was on the main sequence, which means if this star replaced the Sun, its surface would extend nearly to Earth's orbit. The surface temperature has dropped to around 3,500 Kelvin, cool by stellar standards, and the star glows with a deep orange-red light that is characteristic of red giants. The luminosity is about 1,000 times what it was on the main sequence, and the star shines brightly despite its cool surface. The star's outer layers are tenuous and extended, with densities far lower than the main sequence surface, and the material here is only weakly bound by gravity. The escape velocity at the surface is much lower than it was when the star was compact, and material is constantly being lost to space through the stellar wind. The mass loss rate has increased dramatically compared to the main sequence phase, and the star is now losing perhaps 1/10,000th of a solar mass every million years. This may not sound like much, but over the red giant phase, it adds up to a significant fraction of the star's total mass. Looking inward toward the core, the structure is sharply divided into distinct regions. The core is made of helium, inert and not fusing, with a mass of about 1/4 of the star's total mass. The core's temperature has climbed to around 100 million Kelvin. As it continues to contract under gravity, and the density is extraordinarily high, supported by electron degeneracy pressure. Surrounding the core is a thin shell where hydrogen is fusing to helium, and this shell provides essentially all of the star's energy output. Above the shell is the vast envelope of hydrogen-rich gas that extends to the star's surface. The core's temperature is approaching the point where helium can begin to fuse. And helium fusion requires much higher temperatures than hydrogen fusion, because helium nuclei carry twice the electric charge and repel each other more strongly. The fusion of helium into heavier elements proceeds through a process called the triple alpha reaction, where 3 helium nuclei, alpha particles in older terminology, combine to form a carbon nucleus. The process happens in 2 steps. 2 helium nuclei fuse to form beryllium-8, and then a 3rd helium collides with the beryllium before it decays to form carbon-12. The star's surface shows signs of the vigorous convection happening in the outer envelope, with the entire outer half of the star's mass circulating in convective cells. Hot material rises from below the surface, reaches the surface where it radiates energy into space, and cools, then sinks back down to be reheated. The convection creates temperature and density variations on the surface, and the surface appears mottled with brighter and darker regions. The convection also brings material from deep inside the star to the surface, and elements created in the star's core by fusion can now appear in the star's spectrum. Time continues forward, and the core temperature climbs the last few million degrees toward the helium fusion threshold, passing 90 million Kelvin and approaching 100 million. The core is extremely dense now, about 100,000 times the density of water, and the helium nuclei are pressed close together by the weight of the layers above. The electron degeneracy pressure holds the core up against gravity's crushing force, but the pressure does not increase with temperature. This decoupling of pressure and temperature will lead to dramatic consequences when fusion ignites. In the core of this particular star, which has a mass similar to the Sun, the helium ignition will occur suddenly in an event called the helium flash. The flash happens because the core is degenerate, meaning the pressure does not respond to temperature changes. When helium fusion begins and generates heat, the temperature rises, but the pressure does not increase, so the core does not expand and cool as it would in a normal gas. Instead, the temperature keeps rising, and the fusion rate accelerates in a runaway process. The moment arrives without warning to an outside observer, and deep in the core, the temperature crosses 100 million Kelvin, and helium fusion begins. The initial fusion reactions release energy that heats the surrounding helium, and the higher temperature causes more fusion, which generates more heat, which causes even more fusion. Within seconds, the fusion rate in the core skyrockets, and the energy generation reaches levels billions of times higher than the star's normal luminosity. The helium flash is underway, a thermonuclear runaway happening in the degenerate core. Fortunately for the star, the flash happens deep inside, where the enormous energy release cannot escape directly to the surface. The energy from the flash goes into heating the core, and as the temperature rises past 100 million Kelvin towards several hundred million Kelvin, the degeneracy begins to lift. The electrons gain enough thermal energy that degeneracy pressure is no longer the dominant support mechanism, and normal gas pressure starts to contribute. Once normal pressure takes over, the core expands in response to the heating, and the expansion cools the core and slows the fusion rate. The runaway stops, and fusion settles into a stable state. The entire helium flash lasts only a few minutes, far too brief to be visible from outside the star as a change in luminosity or appearance. But it fundamentally alters the star's internal structure. The core is now actively fusing helium into carbon through the triple alpha process, and this fusion generates energy that supports the core against further contraction. The core expands slightly from the flash, which reduces the temperature and pressure in the hydrogen-burning shell above it. The shell burning rate decreases, and the star's total energy output actually drops, despite the core now generating energy again. The star responds to the reduced energy output by contracting slightly, and the surface shrinks from its maximum red giant size. The radius decreases from 100 solar radii to perhaps 10 or 15 solar radii, still much larger than the main sequence, but noticeably smaller than the red giant maximum. The surface temperature increases as the surface area decreases, and the color shifts from deep red toward orange or even yellow. The star settles into a new equilibrium configuration with two active fusion zones, helium fusing to carbon in the core and hydrogen fusing to helium in a shell around the core. You observe the star in its new configuration, now burning helium in the core and hydrogen in a shell, and the structure is more complex than it was during the main sequence. The helium burning releases energy through the triple alpha process, combining 3 helium nuclei to form 1 carbon nuclei, and some of the carbon nuclei capture additional helium to form oxygen. The core is gradually building up a mixture of carbon and oxygen. The ash from helium fusion and this carbon-oxygen mixture will accumulate just as helium accumulated during hydrogen burning. The helium burning phase is much shorter than the hydrogen burning phase was, because helium fusion releases less energy per unit mass than hydrogen fusion, and because the core's helium supply is much smaller than the original hydrogen supply. The star will burn helium in its core for about 100 million years, roughly 1% of the time it's spent on the main sequence. The brevity of this phase means that far fewer stars are observed in the helium burning phase than in the hydrogen burning phase, making helium burning giants less common in surveys. The star's position on an astronomer's Hertzsprung-Russell diagram has changed dramatically from the main sequence to the red giant branch, and now to the horizontal branch where helium-burning stars reside. The horizontal branch is so named because stars of different masses, but all burning helium in their cores, have similar luminosities and cluster around a horizontal line on the diagram. The star is now less luminous than it was at the tip of the red giant branch, but still much more luminous than it was on the main sequence. The stellar wind continues to strip mass from the star's outer layers, and the wind is enriched with elements created inside the star and brought to the surface by convection. Carbon from helium fusion appears in the wind, mixed with hydrogen and helium, and traces of nitrogen from the CNO cycle that operated during hydrogen burning. This enriched material flows into the interstellar medium, eventually to be incorporated into future generations of stars and planets. The star is contributing to the chemical evolution of the galaxy. Time passes, and the helium in the core is steadily converted to carbon and oxygen, just as hydrogen was converted to helium before. The helium burning proceeds at a rate that balances the star's luminosity, and the core conditions remain relatively stable, with temperature around 100 million Kelvin and density about 10,000 times that of water. The carbon-oxygen core grows slowly as helium fusion adds to it from above, and eventually the helium fuel in the core will run low, just as hydrogen did billions of years ago. The star's appearance has stabilized in this helium-burning configuration, and to an outside observer, it would look like a moderately large orange or yellow giant star, smaller than the largest red giants, but still much bigger than main sequence stars. The surface temperature is around 5,000 Kelvin, warm enough to glow yellow or orange, and the luminosity is steady at perhaps 50 times the main sequence value. The star is in a brief, stable period before the next phase of rapid evolution begins. Around the star, any surviving planets have experienced dramatic changes as the star evolved from main sequence to red giant and then contracted again during helium ignition. Planets that were once in the habitable zone were first roasted by the red giant phase and then experienced changing conditions as the star's luminosity fluctuated. The outer planets, if any exist, have been warmed by the star's increased luminosity, and moons in the outer system might have become temporarily habitable as ice melted and atmospheres thickened. The star's evolution creates a moving habitable zone that sweeps outward and affects different regions of the planetary system at different times. The helium burning phase is a brief respite in the star's evolution, a temporary return to stable fusion-powered structure after the runaway of the helium flash. The star will remain in this state for about 100 million years, a long time by human standards, but short compared to the billions of years already past. The core is generating energy again, and the structure is temporarily stable, but the helium fuel is finite and will eventually run out. When it does, the star will face another transition, and the next phase will be the last before the star sheds its envelope and dies. The helium burning in the core has proceeded for about 100 million years, and the helium fuel is now running low, just as the hydrogen fuel did billions of years earlier. The core has converted most of its helium into carbon and oxygen, and these elements cannot fuse at the current core temperature of around 100 million Kelvin. Carbon fusion would require temperatures of about 600 million Kelvin, far hotter than this star's core can reach, and so the carbon-oxygen mixture accumulates as inert ash in the center. The star's mass is not high enough to compress and heat the core to the temperatures needed for carbon fusion, and this limitation will determine the star's ultimate fate. As the core helium depletes, fusion reactions move outward into a shell around the carbon-oxygen core, similar to what happened when hydrogen in the core was exhausted. The helium shell burning surrounds the inert carbon-oxygen core, and above the helium shell, the hydrogen shell continues to burn as well. The star now has two active fusion shells, helium fusing to carbon and oxygen in the inner shell, and hydrogen fusing to helium in the outer shell, with an inert carbon-oxygen core at the center and a vast hydrogen envelope above. From your observing position, the star is beginning to expand again as the dual shell burning configuration generates more energy than the stable helium core burning did. The increased energy output pushes the outer layers outward, and the radius grows from 10 or 15 solar radii back toward larger values. The star is ascending the asymptotic giant branch, the final phase of substantial evolution before mass loss expels the envelope. The asymptotic giant branch is similar to the earlier red giant branch, but the star is more luminous, and the internal structure is more complex. The helium shell burning is unstable in a way that hydrogen shell burning is not, and the instability leads to thermal pulses that occur every few tens of thousands of years. A thermal pulse happens when helium builds up in the layer between the hydrogen shell and the helium shell. And when enough helium accumulates, the shell fusion rate suddenly increases. The pulse generates a huge amount of energy over a short time, perhaps a few hundred years, and the energy pulse travels outward through the star. The pulse temporarily shuts off the hydrogen shell burning above it and causes the star's luminosity to vary significantly. You can observe these thermal pulses as variations in the star's brightness and radius, the star swelling and brightening during and after each pulse, and then settling back down before the next pulse. The pulses create dramatic internal changes, temporarily mixing material from deep inside the star and bringing carbon and other fusion products to the surface. After each pulse, convection dredges material from near the helium shell up to the surface, enriching the outer layers with carbon and other heavy elements. The star's surface composition changes noticeably, and carbon becomes more abundant relative to oxygen. The star's radius has grown to around 200 times its main sequence value during this asymptotic giant branch phase, and the surface temperature has dropped to around 3000 Kelvin. The star glows deep red, much redder than it was during the earlier red giant phase, and the luminosity is thousands of times the main sequence value. The star is enormous and luminous, one of the brightest stars in this phase, though the phase will not last long because the mass loss is accelerating dramatically. The mass loss rate has increased to about 100,000th of a solar mass per year, which is 1,000 times higher than it was during the main sequence. At this rate, the star is losing 1 Earth mass of material every few hundred years, and the accumulated mass loss is stripping away the outer layers. The stellar wind is strong, driven by radiation pressure on dust grains that form in the cool outer atmosphere, and the wind carries away the hydrogen-rich envelope that surrounds the fusion shells and the core. The thermal pulses continue every 20,000 to 100,000 years, and each pulse temporarily boosts the mass loss rate even higher. During and after a pulse, the star can lose mass at rates up to 1/10,000th of a solar mass per year, and these periods of enhanced mass loss are called superwinds. The superwind strips away substantial amounts of material, and over the course of a few million years, the star loses most of its hydrogen envelope. The mass loss is so extreme that the fusion shells are gradually exposed as the overlying material is removed. Looking inward at the star's structure, you can see the carbon-oxygen core at the center, inert and supported by electron degeneracy pressure, with a mass of about half to 60% of the star's remaining mass. Around the core are the 2 fusion shells, thin regions where helium and hydrogen burn in shells, generating energy and adding to the core from below, and creating helium from above. The shells are very thin compared to the star's radius, and above them is the remaining envelope, now much less massive than it was originally. The envelope is being expelled into space at an accelerating rate, and the material forms an expanding shell around the star. The expelled gas is moving outward at about 10 to 30 kilometers per second, slow compared to explosive events, but fast enough to cover large distances over thousands of years. The shell of expelled material is still relatively dense close to the star, but it becomes thinner as it expands and spreads over a larger area. The star's luminosity is now thousands of times higher than it was on the main sequence, and the energy generated by the two fusion shells is enormous despite the shells being so thin. The energy flows outward through the remaining envelope and is radiated from the huge surface into space. The star is one of the most luminous objects in the galaxy for its mass, though it is still far less luminous than the truly massive stars that can reach millions of times the sun's luminosity. The thermal pulses bring more than just carbon to the surface, and some pulses dredge up trace amounts of even heavier elements created by neutron capture in the helium shell. These elements include barium, technetium, and other heavy elements that do not exist in nature on Earth because they are radioactive and decay over time. The detection of technetium in a star's spectrum is proof that the element was recently created in the star's interior, because technetium's half-life is so short that it could not have been present since the star formed. The star has become what astronomers call a carbon star, with more carbon than oxygen in its outer layers. And the carbon creates molecules in the cool atmosphere that change the star's appearance and spectrum. Carbon molecules, like carbon monoxide and various carbon chains, form in the atmosphere, and these molecules absorb light at specific wavelengths, creating distinctive spectral features. Some of the carbon condenses into soot particles in the outer atmosphere, and these particles are lifted away by radiation pressure, contributing to the mass loss. You watch as the mass loss accelerates further, and the envelope that once contained most of the star's mass is now largely gone, blown away into space by the wind and the thermal pulses. The fusion shells are approaching the surface, no longer buried deep inside the star, but rather close to the outer edge. The remaining envelope is thin, perhaps only a few % of the original mass, and it will be expelled completely over the next few thousand years. The expelled material is accumulating in a shell around the star, and the shell is now large enough and distinct enough to be visible as a nebula if you were far enough away to see it. The shell is expanding outward at tens of kilometers per second, and it contains several tenths of a solar mass of gas, enriched with the products of fusion. The material includes hydrogen and helium from the original star, carbon and oxygen from helium fusion, nitrogen from hydrogen fusion via the CNO cycle, and traces of heavier elements from neutron capture. The star is nearing the end of its asymptotic giant branch phase, and the final mass loss event is approaching. The envelope will be completely expelled over the next few thousand years, and when it is gone, the hot core and fusion shells will be exposed. The exposed core will be hot enough to ionize the surrounding expelled gas with its ultraviolet radiation, and the ionized gas will glow brightly in emission lines. A planetary nebula will form, one of the most beautiful phenomena in the galaxy, and it will mark the star's transition from giant to white dwarf. The thermal pulses have stopped now because the helium shell has run out of fuel and can no longer sustain burning. The hydrogen shell is still active, but barely, and it too will shut down as the last of the envelope is expelled and the shell runs out of overlying material. The star is coasting on the energy stored in its structure, and it is contracting as the envelope disperses. The surface temperature is rising as the outer layers are removed and the hot interior becomes visible. The transition from asymptotic giant branch star to planetary nebula happens quickly by stellar standards, taking only a few thousand years, and the change is dramatic. The star evolves from a cool red giant to a hot central star in this brief period, and the expelled material transforms from an expanding wind into a glowing nebula as the central star's temperature rises. You are witnessing the final phase of the star's active evolution, the last burst of change before it settles into its final state, as a white dwarf cooling in the center of the nebula it created. The final remnants of the star's envelope are being expelled now, and the mass loss has reached its peak in what is often called the superwind phase. Material is streaming away from the star at rates approaching 1/10,000th of a solar mass per year, and the hydrogen-rich outer layers are being stripped away completely. The star's radius is shrinking as the envelope disperses, and the hot interior is becoming exposed. The surface temperature is rising rapidly as the outer cool layers are removed, climbing from 3,000 Kelvin towards 10,000 Kelvin and higher. From your position, observing the star, you can see the expelled material forming a distinct shell around the star, a bubble of gas expanding outward in all directions. The shell is denser in some directions than others, because the mass loss was not perfectly spherical. And the result is that the shell has structure with thicker regions and thinner regions. The asymmetries may be caused by the star's rotation, by magnetic fields, or by the presence of a companion star, if one exists. These asymmetries will shape the final appearance of the planetary nebula. The shell continues to expand, driven by the momentum of the stellar wind and by the pressure of newly expelled material pushing on the older material ahead of it. The expansion velocity is about 20 kilometers per second on average, which means the shell is growing by about 600 million kilometers per year. After 1,000 years, the shell will be about 1/10 of a light year across, and after 10,000 years, it will be close to 1 light year. The shell is becoming a planetary nebula, though the nebula will not be visible until the central star becomes hot enough to ionize the gas. The star at the center of the expanding shell is contracting rapidly now that it has lost the envelope, and it is transitioning from a cool giant to a hot compact object. The fusion shells that were generating energy have shut down as the overlying material was expelled, and the star is no longer generating energy through fusion. The only energy source is the residual heat in the star's interior, and the star is essentially coasting on stored thermal energy. The contraction converts gravitational potential energy into heat, keeping the star hot even without fusion. The central star's surface temperature climbs past 20,000 Kelvin and then 50,000 Kelvin as the star contracts and the hot interior becomes fully exposed. The star is now emitting most of its light in ultraviolet wavelengths, invisible to human eyes, but incredibly energetic. The ultraviolet photons stream outward from the hot star and encounter the expanding shell of gas that was expelled earlier. When the ultraviolet photons strike atoms in the shell, they ionize the atoms, stripping electrons away and leaving the atoms electrically charged. The ionization process creates a bubble of ionized gas around the central star, and as the bubble grows, it catches up with the expanding shell and begins to ionize it. The ionized gas responds to the ultraviolet radiation by emitting light at specific wavelengths corresponding to the emission lines of hydrogen, helium, oxygen, nitrogen, and other elements. The emission is strong in certain wavelengths, like H alpha, red, and OI3, blue-green. And these colors give planetary nebulae their characteristic appearance. The nebula begins to glow, and the planetary nebula becomes visible. You are now witnessing the planetary nebula in its full glory, an expanding shell of ionized gas, glowing in brilliant colors around the hot central star. The nebula is not uniform, but rather shows complex structure with shells, rings, lobes, and filaments depending on how the mass loss occurred and how the ionization front propagated through the gas. Some planetary nebulae appear circular or spherical, while others are elongated or bipolar, with two lobes extending in opposite directions. This nebula shows a roughly spherical shell, with some asymmetry, brighter in some regions than others. The colors visible in the nebula come from the specific emission lines of various elements, and each color corresponds to a particular transition in a particular atom. The red color comes primarily from H-alpha emission, the transition where hydrogen electrons drop from the third to the second energy level. The blue-green color comes from doubly ionized oxygen, O3I, and the green color from this element is often the brightest feature in planetary nebulae. Nitrogen, sulfur, and other elements contribute additional colors and structure. The central star continues to heat as it contracts, and the surface temperature reaches 100,000 Kelvin or more, making it one of the hottest stars in the galaxy. The star is now very small, approaching the size it will have as a white dwarf, perhaps similar to Earth's size. The luminosity is high because the surface is so hot, even though the surface area is small. The star is transitioning towards its final state, the white dwarf phase, and the planetary nebula marks this transition. The nebula expands steadily, growing larger as years and then centuries pass, and the central star continues to contract and heat initially, before eventually beginning to cool. The ionization of the gas in the nebula requires continuous ultraviolet radiation from the central star, and as long as the star remains hot enough, the nebula will glow. The nebula will remain visible for tens of thousands of years before it expands so much that the gas becomes too thin to emit visible light. The central star will cool during this time, and its ultraviolet output will decrease, eventually no longer sufficient to ionize the gas. Looking at the structure of the nebula, you can see multiple shells representing different episodes of mass loss during the late asymptotic giant branch phase. The innermost shell is denser and brighter, created by the most recent mass loss, while outer shells are fainter and more diffuse, created by earlier mass loss episodes. The shells are expanding at slightly different velocities, and over time they will interact as the faster inner shells catch up with the slower outer shells. These interactions can create shock waves that brighten regions of the nebula and create fine filamentary structures. The planetary nebula is dispersing material into the interstellar medium, enriching it with the products of stellar nucleosynthesis. The nebula contains carbon and oxygen, created by helium fusion, nitrogen enhanced by the CNO cycle, and traces of heavier elements created by neutron capture processes. This material will eventually mix with the general interstellar gas and dust, and future generations of stars will form from material enriched by this and countless other planetary nebulae. The cycle of stellar birth, life, and death is a recycling process that gradually increases the abundance of heavy elements in the galaxy. The total mass of the nebula is about half a solar mass, representing the envelope that was expelled from the star during the late giant phases. The remaining mass of the central star is about half a solar mass as well, and this core is what will become the white dwarf. The star has lost roughly half its original mass over its lifetime, most of it during the final few million years of the giant phases. The mass loss has been gradual during most of the star's life, but accelerated dramatically at the end. The central star's contraction is slowing now because electron degeneracy pressure is becoming important, and the core is reaching the configuration it will have as a white dwarf. The degeneracy pressure provides support against gravity without requiring high temperature, and the star can remain in this state essentially forever because degeneracy pressure does not depend on an energy source. The star has reached the end of its fusion-powered evolution, and it will now simply cool as a white dwarf over billions of years. The planetary nebula around the star is one of thousands or tens of thousands in the galaxy at any given time, and they are among the most beautiful astronomical objects visible to telescopes. Each planetary nebula is unique, with its own shape, structure, and color distribution determined by the details of how the central star lost its mass and how the ionization proceeded. Famous planetary nebulae include the Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, and the Dumbbell Nebula, each with distinctive appearance. The lifetime of a planetary nebula as a visible object is relatively short, about 10,000 to 50,000 years, because the gas expands and becomes too diffuse to glow brightly, and the central star cools and stops providing enough ultraviolet radiation to ionize the gas. After this time, the nebula fades from view and merges with the interstellar medium, and only the white dwarf remains visible. The planetary nebula phase is a brief but spectacular finale to the star's active life. You watch as the nebula continues to expand and evolve, the central star slowly cooling, and the colors and structures changing over thousands of years. The nebula is a memorial to the star that created it, a glowing testament to billions of years of fusion and evolution. The star has completed its journey from molecular cloud to main sequence, to giant to planetary nebula, and what remains is the core, soon to be fully revealed as a white dwarf, the final endpoint of the star's evolution. The expelled gas carries with it the history of the star's nucleosynthesis, atoms that were created from simpler atoms through fusion, and these atoms will eventually become part of new stars and planets. Some of the carbon in your body, if you were a real observer, was likely created in stars like this. One, fused from helium in the core of a dying star, and expelled in a planetary nebula billions of years ago. The connection between stellar evolution and the material world is direct and profound. As the nebula fades and the central star cools, the active phase of this star's life comes to an end. The fusion reactions that powered the star for billions of years have ceased. The envelope has been dispersed, and only the core remains. The white dwarf sits at the center of the fading nebula, no longer generating energy, simply radiating away the heat stored in its interior. The transformation from star to stellar remnant is complete, and the long cooling phase begins. The planetary nebula has dispersed into the interstellar medium over the past tens of thousands of years, fading as the gas expanded and thinned, and as the central star cooled and reduced its ultraviolet output. What remains visible now is the white dwarf, the exposed core of the original star, a small, dense object that represents the endpoint of stellar evolution for stars like this one. The white dwarf is roughly the size of Earth, about 12,000 kilometers in diameter, but it contains about half a solar mass of material compressed into that small volume. The density is extraordinary, about 1 million grams per cubic centimeter, which means a teaspoon of white dwarf material would weigh about 5 tons on Earth. From your observing position, the white dwarf appears as a small brilliant point of light, much smaller than the original star, but intensely bright because its surface temperature is still very high. The surface temperature is currently around 100,000 Kelvin, though it is falling as the white dwarf radiates energy into space. The white dwarf glows blue-white from this high temperature, and its luminosity is still substantial, despite its small size. Over time, the temperature will drop, and the color will shift from blue-white to white, and then to yellow, and eventually to red as the white dwarf cools. The white dwarf's composition reflects its formation history. And for this star, the white dwarf is made primarily of carbon and oxygen, created during helium fusion in the core. The carbon and oxygen are not mixed uniformly, but rather stratified, with carbon dominating in the center and oxygen more abundant in the outer layers. The surface of the white dwarf may have a thin layer of helium from the remnants of the helium-burning shell, and above that might be an even thinner layer of hydrogen if any envelope material remained. The layers are stable and do not mix because the star has no convection or other mixing processes. The structure of the white dwarf is unlike anything in everyday experience, and the material inside is in a state called electron-degenerate matter. The atoms have been completely ionized by the intense heat, and the electrons and nuclei are separated into a plasma. The electrons are packed so closely together that quantum mechanics forces them into high-energy states because the Pauli exclusion principle prevents more than one electron from occupying the same quantum state. The resulting electron degeneracy pressure is what supports the white dwarf against gravitational collapse. The electron degeneracy pressure does not depend on temperature, which means the white dwarf's structure is stable even as it cools. A normal gas would contract and heat up as it cooled and lost pressure, but a degenerate gas maintains its pressure regardless of temperature. This unusual property means the white dwarf can cool essentially forever without collapsing further, and it will remain at roughly Earth's size indefinitely. The white dwarf has reached a stable configuration that requires no energy input to maintain. The white dwarf is not generating energy through fusion or any other nuclear process, and the energy it radiates comes entirely from the thermal energy stored in the nuclei and in the non-degenerate ions in the interior. As this heat radiates away, the white dwarf cools, and the cooling happens slowly because the white dwarf has a large heat capacity and a small surface area through which to radiate. The cooling timescale is billions of years, and the white dwarf will remain visible for a substantial fraction of the age of the universe. Looking at the white dwarf, you can see that it has no surface features in the way the original star did. There are no sunspots, no granulation, no active regions. The surface is smooth and featureless, glowing uniformly at its high temperature. The gravity at the surface is immense, about 300,000 times stronger than Earth's surface gravity, and the escape velocity is about 5,000 kilometers per second, several percent of the speed of light. Anything on the surface would be crushed by the intense gravity, and light itself is redshifted as it climbs out of the white dwarf's gravitational well. The white dwarf's mass is constrained by a fundamental limit called the Chandrasekhar limit, which states that electron degeneracy pressure can support a maximum mass of about 1.4 solar masses. White dwarfs more massive than this limit cannot exist stably because the degeneracy pressure is insufficient to hold up the weight, and the star collapses further to become a neutron star or black hole. This white dwarf has a mass well below the limit at about 0.5 solar masses, so it is stable and will remain so indefinitely. The white dwarf rotates, spinning on its axis once every few hours or days, depending on how much angular momentum was retained during the formation process. The rotation is much faster than the original star's rotation, because as the star contracted, its rotation sped up to conserve angular momentum. The same process that makes figure skaters spin faster when they pull in their arms. Some white dwarfs rotate very rapidly, spinning in seconds or minutes, especially if they formed from stars that were already rotating quickly, or if they accreted angular momentum from a companion. Some white dwarfs show periodic variations in brightness, called pulsations, and these white dwarfs are classified as ZZ Ceti variables or other types depending on their temperature and pulsation characteristics. The pulsations are caused by oscillations in the white dwarf structure, where regions of the star expand and contract in regular patterns. The pulsations provide a way to study the white dwarf's interior, because the oscillation frequencies depend on the internal structure and composition. This white dwarf may develop pulsations as it cools through certain temperature ranges. The white dwarf is isolated now, no longer surrounded by planets or a disk, though some white dwarfs show evidence of rocky debris from destroyed planets or asteroids. The intense gravity of the white dwarf during its formation may have disrupted any planets that were too close, and the planets that were farther out may have been flung into distant orbits or ejected from the system entirely. Some white dwarfs show metal lines in their spectra, indicating that rocky material is falling onto the star, possibly from asteroids or comets, perturbed into star-crossing orbits. The white dwarf's magnetic field can be strong, sometimes millions of times stronger than Earth's magnetic field, though this white dwarf has a more modest field. The strong magnetic fields in some white dwarfs are thought to be the result of magnetic flux being conserved as the star contracted and the field is frozen into the conducting plasma. The magnetic field affects the star's atmosphere and can channel material falling onto the star in binary systems where the white dwarf is accreting from a companion. Over time, the white dwarf cools from 100,000 Kelvin toward lower temperatures, and the cooling follows a predictable track determined by the white dwarf's mass and composition. The surface temperature drops by about a factor of 2 over the first billion years, and then the cooling slows as the white dwarf enters the regime where crystallization begins to matter. When the interior temperature drops low enough, the carbon and oxygen nuclei begin to arrange themselves in a crystal lattice, and the white dwarf core starts to solidify from the inside out. The crystallization process releases latent heat, similar to how water releases heat when it freezes, and this heat slightly slows the cooling process. The white dwarf is essentially becoming a giant crystal, with carbon and oxygen atoms arranged in a regular geometric pattern, like a diamond. The crystallization starts in the core, where the temperature is lowest. Surprisingly, the core is cooler than the surface in a white dwarf, because heat flows from inside to outside and progresses outward over billions of years. You observe the white dwarf as it cools through various temperature stages, the color shifting from blue-white to white, and then to yellow as thousands and millions of years pass. The luminosity decreases as the surface temperature drops, because the star radiates less energy at lower temperatures, and the surface area remains roughly constant. Eventually, the white dwarf will become too faint to see easily with optical telescopes, though it will still be detectable in infrared wavelengths, where cooler objects emit most of their radiation. The white dwarf is now one of billions in the galaxy, the remnants of all the sun-like stars that have lived and died over the galaxy's history. White dwarfs accumulate over time because they last essentially forever, and the galaxy's population of white dwarfs is a record of billions of years of stellar evolution. The oldest white dwarfs in the galaxy have been cooling for over 10 billion years, and they are very faint and cool, with surface temperatures of only a few thousand Kelvin. The white dwarf's fate is to cool slowly over trillions of years, eventually becoming a black dwarf, a theoretical object so cool it emits negligible radiation and is essentially invisible. The universe is not old enough for any black dwarfs to exist yet, as even the oldest white dwarfs are still warm enough to emit detectable light. The cooling time to reach near absolute zero temperatures is so long that it exceeds the current age of the universe by factors of thousands or more. You watch as the white dwarf continues its slow fade, the surface temperature dropping toward 10,000 Kelvin and then lower, the color becoming yellow and then orange and eventually red over billions of years. The white dwarf is no longer an active star, but a slowly cooling ember, radiating away the heat from its formation and from the billions of years of fusion that preceded it. The transformation from bright blue-white to dim red will take longer than the star spent on the main sequence, and the final cooling to near invisibility will take trillions of years more. The white dwarf has been cooling for billions of years now, and its surface temperature has dropped significantly from the initial 100,000 Kelvin to perhaps 15,000 Kelvin. The color has shifted from blue-white through white and into yellow, and the luminosity has decreased to about 1% of the sun's luminosity. The white dwarf still glows, but it is much fainter than it was when it first formed, and it would be difficult to see from great distances without a telescope. The cooling continues inexorably because there is no energy source to replenish the heat being radiated away. From your observing position, the white dwarf appears as a dim yellowish point of light, small and faint, but still detectable. The size remains the same as it was billions of years ago, about 12,000 kilometers in diameter, because the electron degeneracy pressure that supports the white dwarf does not change significantly as the temperature drops. The mass also remains constant at about half a solar mass, unchanged since the planetary nebula dispersed and left the core behind. The white dwarf is in a stable state that will persist for times far longer than the current age of the universe. The cooling rate has slowed compared to the early stages because cooler objects radiate less energy and because the heat capacity of the degenerate matter is large. The surface temperature drops by about 1,000 Kelvin every billion years at this stage, and the rate will continue to decrease as the white dwarf cools further. The cooling follows a well-understood trajectory determined by the white dwarf's mass and composition. And astronomers can use the cooling curve to estimate the age of a white dwarf from its temperature and luminosity. The interior of the white dwarf has undergone significant changes during the cooling process, and the core is now largely crystallized. The carbon and oxygen nuclei have arranged themselves in a regular crystal lattice, forming what is essentially a gigantic diamond or similar carbon-oxygen crystal, surrounded by a liquid mantle and a thin gaseous atmosphere. The crystallization began in the center where the density is highest and has progressed outward over billions of years. The crystallized core occupies a substantial fraction of the white dwarf's volume now, perhaps half or more. The crystallization process released latent heat when it occurred, and this energy release slightly delayed the cooling at certain temperatures. The effect shows up as a bump in the cooling curve, where white dwarfs spend longer than expected at certain luminosities, because the crystallization energy temporarily supplements the radiated energy. This delay has been observed in populations of white dwarfs and provides confirmation that the crystallization process is real and occurs as predicted by theory. The white dwarf's surface shows some structure now in the form of a thin atmosphere, though calling it an atmosphere is somewhat generous given its thinness. The atmosphere is composed of hydrogen or helium depending on which element remained on the surface after the planetary nebula phase. And it is only a few hundred kilometers thick, with a mass of perhaps 1/10,000th of Earth's mass. The atmosphere is stratified by gravity, with heavier elements sinking and lighter elements rising. So the visible surface is typically pure hydrogen or pure helium, with no heavier elements detectable unless they are continuously supplied. Some white dwarfs show spectral features that indicate metals like calcium, magnesium, or iron in their atmospheres. And these elements must be continuously supplied from outside because they would sink below the visible surface in a matter of days or years due to the intense gravity. The metals are thought to come from rocky material like asteroids or fragments of disrupted planets that fall onto the white dwarf and vaporize in the hot atmosphere. The presence of these metals provides evidence that planetary systems or debris disks can survive around white dwarfs. The white dwarf's temperature continues to drop, passing 10,000 Kelvin and heading toward lower values, and the color shifts from yellow toward orange and then red. The luminosity decreases proportionally to the fourth power of the temperature, according to the Stefan Boltzmann law. So as the temperature drops, the white dwarf fades rapidly. At 10,000 Kelvin, the luminosity is about 1,000th of the sun's, and at 5,000 Kelvin, it will be about 1/10,000th. The white dwarf is disappearing from view, fading into obscurity. You watch the slow evolution over billions of years, as the white dwarf cools from 15,000 Kelvin to 10,000, and then to 7,000 Kelvin, the cooling taking longer and longer for each interval. The surface is now glowing a dull orange red, and the light output is so low that the white dwarf would be invisible to the naked eye, even from nearby. Only in infrared wavelengths does the white dwarf still shine brightly, and infrared telescopes would be needed to detect it against the background sky. The timescale for cooling becomes extraordinarily long as the temperature drops, and the white dwarf will take tens of billions of years to cool, from 10,000 Kelvin to 5,000 Kelvin, and even longer to cool to near absolute zero temperatures. The universe is currently about 14 billion years old, and the white dwarfs that formed from the earliest stars in the galaxy are still relatively warm, with surface temperatures of several thousand Kelvin. No black dwarfs, the theoretical endpoint where a white dwarf is too cool to emit detectable radiation, have formed yet because the universe is too young. The crystallized interior is now essentially a solid throughout most of the white dwarf's volume, with only the outermost layers remaining liquid or gaseous. The crystal lattice is thought to be body-centered cubic for the carbon and oxygen mixture, a geometric arrangement that minimizes energy at these densities and temperatures. The nuclei vibrate around their lattice positions with thermal energy, but they are locked in place by the structure. The white dwarf has become a stellar crystal floating in space, slowly radiating away the last of its heat. Quantum mechanical effects become increasingly important as the white dwarf cools, and eventually processes like quantum tunneling may alter the crystal structure over inconceivably long timescales. Some theories suggest that the carbon and oxygen nuclei might undergo fusion through quantum tunneling over timescales of 10 to the 30 years or more, slowly converting the white dwarf to iron in a process that would release a tiny amount of energy. These timescales are so long that they are almost meaningless, far exceeding the current age of the universe by factors of billions of billions. The white dwarf's rotation has slowed over billions of years due to magnetic braking and other effects, and it now spins perhaps once every few days or weeks, much slower than when it first formed. The slowing is gradual and continues indefinitely, with the rotation period increasing as angular momentum is lost to magnetic fields and gravitational waves. Eventually, over timescales of trillions of years, the white dwarf's rotation will become negligible, and it will essentially stop spinning relative to the surrounding space. Looking at the white dwarf now, you see an object that has cooled to around 5,000 Kelvin, glowing a deep red color and emitting very little visible light. The luminosity is about 1/10,000th of the sun's, and the white dwarf is fading into the background of the galaxy. The surface is featureless, a uniform red glow from the thermal radiation, and there is no activity, no flares, no spots, nothing but the slow emission of stored heat. The concept of a black dwarf, a white dwarf that has cooled to the point where it emits negligible radiation, is theoretical because the universe is not old enough for such objects to exist. Calculations suggest that a white dwarf would take about 10 to the 15 years to cool to a surface temperature near the cosmic microwave background radiation, which is about 3 Kelvin. At that point, the white dwarf would be in thermal equilibrium with the universe and would cool no further unless the universe itself continues to cool. The cooling trajectory extends into the far future, and you can see that the white dwarf will continue to fade over trillions of years until it becomes essentially invisible in all wavelengths. The transformation from bright blue-white to dark invisible object will take longer than the current age of the universe by a factor of about 100, and the final stages of cooling will take even longer. The white dwarf is entering a phase that will last for the remainder of the universe's existence and far beyond. The white dwarf's fate is one of slow, inevitable decline, cooling asymptotically toward absolute zero, but never quite reaching it. The laws of thermodynamics dictate that the white dwarf will continue to radiate energy as long as its temperature is above the surrounding space. And the radiation will continue for time so long that human language and intuition fail to capture the scale. The white dwarf is essentially immortal, surviving long after galaxies have merged and stars have ceased to form. In the far future, if proton decay occurs as some theories predict, the white dwarf's matter might slowly evaporate as protons decay into lighter particles over timescales of 10 to the 40 years or more. If protons are stable, the white dwarf might instead undergo gradual collapse through quantum tunneling processes over even longer timescales, slowly converting to a neutron star or black hole through quantum effects. These processes are so speculative and occur on such unimaginable timescales that they are more science fiction than science, but they represent the ultimate fate of matter itself. You observe the white dwarf as it cools toward 4,000 Kelvin, and then 3,000. The color now a very dim red, barely visible at all. The luminosity has dropped to 100,000th of the sun's, and the white dwarf is one of the dimmest objects in the galaxy for its mass. The cooling continues, unstoppable and inevitable, as the white dwarf fades towards its final dark state over trillions of years. The transformation from star to stellar remnant to crystal to dark ember is nearly complete in the observational sense, though the final cooling will take far longer than any observation could encompass. The white dwarf has cooled to around 3,000 Kelvin now, and at this temperature, it emits almost no visible light, glowing very faintly in deep red and infrared wavelengths. The luminosity is about 1/1,000,000th of the sun's luminosity, and the white dwarf is effectively invisible to optical telescopes from any significant distance. This is the black dwarf regime, though the term is somewhat premature because the universe is not yet old enough for any white dwarfs to have cooled to near absolute zero temperatures. The white dwarf is approaching the theoretical endpoint of stellar evolution, the final state where no further changes occur except the slow cooling toward thermal equilibrium with the cosmos. From your position, observing this dim ember of a once bright star, you can reflect on the complete life cycle you have witnessed. The star began as a concentration in a cold molecular cloud, a slight density enhancement that gravity amplified into a collapsing core. The collapse took hundreds of thousands of years, and it created a protostar that glowed from compression heat while it waited for fusion to ignite. Fusion began when the core reached 15 million Kelvin, and the star spent 10 billion years on the main sequence converting hydrogen to helium in its core. When the core hydrogen ran out, the star left the main sequence and became a red giant, swelling to 100 times its original size and shining with 1,000 times its original luminosity. Helium fusion ignited in a flash when the core reached 100 million Kelvin, and the star burned helium for 100 million years, while also burning hydrogen in a shell. The helium fuel exhausted, and the star climbed the asymptotic giant branch, becoming even larger and more luminous, while burning in two shells around an inert carbon-oxygen core. The star's outer envelope was expelled through a strong stellar wind, and the material formed an expanding shell that became a planetary nebula when the hot core's ultraviolet light began to ionize it. The planetary nebula expanded for tens of thousands of years, dispersing the outer layers into space and leaving the core exposed as a white dwarf. The white dwarf has been cooling ever since, radiating away its stored heat with no new energy being generated in its interior. The crystalline structure inside the white dwarf is complete now, and the carbon and oxygen atoms are locked in a perfect geometric lattice that extends through most of the star's interior. The electrons remain degenerate, providing the pressure that keeps the white dwarf from collapsing further under its own gravity. The surface has cooled to the point where it emits primarily infrared radiation, and the cooling will continue for trillions of years more. The black dwarf state represents the final resting place for stars like the Sun, the ultimate end of nuclear fusion and stellar activity. Looking at this dark remnant floating in space, you can consider what happens on even longer timescales that stretch beyond current understanding. The white dwarf will continue cooling toward absolute zero, though reaching that temperature would take far longer than the current age of the universe. Some theoretical models suggest that after unimaginable spans of time, quantum tunneling might convert the white dwarf's matter into iron, the most stable element. Other models propose that proton decay might eventually disintegrate the white dwarf entirely, though proton decay has never been observed and may not occur at all. These far future scenarios remain speculative, and they involve timescales so vast that the numbers lose practical meaning. What matters for understanding the star's life is that fusion has ended, the energy has been radiated away, and the remnant will persist essentially unchanged for longer than stars will continue forming in the universe. The white dwarf represents a permanent endpoint for this particular concentration of matter, frozen in a configuration that will outlast galaxies as we know them. But the star's influence extends far beyond its remnant core, and the true legacy lies in what was dispersed rather than what remains. The planetary nebula carried away more than half the star's original mass, and that material spread into the surrounding interstellar medium over thousands of years. The gas contained carbon, created during helium fusion, oxygen created when helium fused with carbon, and nitrogen created through the carbon-nitrogen-oxygen cycle during hydrogen burning. These elements did not exist when the star formed, and they were created through nuclear fusion in the star's core and shells. The expelled material mixes with the hydrogen and helium that fill the space between stars, enriching the interstellar medium with heavier elements. The enriched gas eventually becomes part of new molecular clouds, and those clouds collapse to form new generations of stars. The new stars incorporate the carbon and oxygen from previous stellar generations, and if planets form around them, those planets contain material that was forged in stars that died before the planetary system existed. You are observing this process from a perspective that spans billions of years, watching as the dispersed nebula fades into invisibility and mixes with surrounding gas. The carbon and oxygen atoms that spent billions of years locked in the star's core are now spreading through space, and they will eventually become part of something new. Some atoms may end up in the atmosphere of a gas giant planet, while others may be incorporated into rock or ice in a planetary system that forms millions of years from now. This recycling process has been occurring throughout the history of the universe, and it explains the composition of everything around us, including Earth and the life it supports. The first stars contained only hydrogen and helium, because those were the only elements created in the Big Bang. Those stars produced carbon, oxygen, and other elements through fusion, and when they died, they released those elements into space. Later generations of stars formed from enriched material, and they produced even more heavy elements through their own fusion processes. Our Sun is a relatively late generation star, and it contains about 2% heavy elements by mass, including all the carbon, oxygen, silicon, iron, and other elements that make up Earth and everything on it. The Sun formed from a molecular cloud that had been enriched by countless previous stellar generations, and the planets formed from the disk of material around the young Sun. Every atom heavier than helium in your body was created inside a star that existed before the Sun formed, and those atoms were dispersed when that star died. Standing here in space, observing the cooling white dwarf, you can trace the connection between this stellar remnant and your own existence. The process you have witnessed from beginning to end is the same process that created the building blocks of planets and life. Stars are not separate from us, but rather the source of the material complexity that makes chemistry and biology possible. The universe started with hydrogen and helium, and stars transformed that simple material into the diverse elements that fill the periodic table. The white dwarf ahead of you represents the endpoint of one star's journey, but the atoms it created and dispersed will continue their own journeys for as long as the universe exists. Some of those atoms are already part of new stars that formed after the planetary nebula dispersed. Others are still floating in interstellar space, waiting to be incorporated into future stellar systems. The material is not destroyed, but rather redistributed, and the cycle continues as long as gas remains available for star formation. Looking beyond this individual star, you can see that the galaxy contains hundreds of billions of stars at various stages of this same life cycle. Some are still forming in molecular clouds, some are on the main sequence burning hydrogen, some are red giants approaching the end of their fusion burning phases, and some are white dwarfs cooling in the darkness. The galaxy's appearance is shaped by this continuous cycle of stellar birth and death, with young stars providing the bright blue light of star-forming regions and old stars populating the quieter regions where star formation has ceased. The Sun is currently about halfway through its main sequence lifetime, with roughly 5 billion years remaining before it begins the transition to a red giant. When that time comes, the Sun will follow the same path you have witnessed here, swelling to engulf the inner planets and eventually expelling its outer layers to form a planetary nebula. The Earth may be destroyed during the red giant phase, or it may survive as a scorched dead world orbiting a white dwarf. Either way, the solar system as we know it will end when the Sun exhausts its fuel. But that end point lies billions of years in the future, and for now the Sun remains stable and steady on the main sequence. The stellar life cycle you have witnessed operates on timescales that dwarf human history and even geological time on Earth. Stars change slowly from our perspective, and the Sun will appear essentially unchanged for millions of years into the future. The stability of stars during their main sequence phase is what allows planets to maintain stable conditions long enough for life to develop and evolve. The white dwarf continues its slow fade into darkness, and the space around it is quiet and still. The planetary nebula has long since dispersed, and the enriched gas has mixed with the interstellar medium and become indistinguishable from the surrounding material. The star that once shone brightly for billions of years is now a faint ember that will eventually become invisible. The journey from cloud to dwarf has taken longer than the Earth has existed, and the cooling phase will take far longer still. Your journey through the star's life has shown you the processes that shape the universe on its largest scales. Stars are the factories where elements are made, and their life cycles determine the chemical evolution of galaxies over cosmic time. The early universe contained only the simplest elements, but billions of years of stellar evolution have enriched the cosmos with the building blocks of complexity. Every rocky planet, every molecule of water, every carbon-based life form owes its existence to fusion reactions in stars that lived and died over the history of the universe. The complete life cycle from molecular cloud to black dwarf represents one of nature's fundamental processes, repeated countless times across the cosmos, in every galaxy. The specific details vary depending on the star's mass, but the basic pattern remains the same for all stars in a similar mass range. More massive stars follow different paths, involving supernovae and neutron stars or black holes, while less massive red dwarfs burn so slowly they will outlive the current age of the universe. But for sun-like stars, the journey you have witnessed is the complete story from beginning to end. The white dwarf floats silently in space, dark and dense, a monument to the star that once was. The universe continues around it, new stars forming while old stars die, and the cycle repeats across billions of years. You have witnessed one complete cycle, one star's journey through existence. And in doing so, you have seen the process that shapes everything we know. The journey is complete, and the star has reached its final rest.